Hello future engineers, subscribers, viewers, and students. There is another video in calculus, particularly on finding equations of tangents to curves and one interpretation of first derivative, which is not only slope of tangent to the curve, but the instantaneous velocity of a particle, instantaneous velocity of a particle on the position versus time curve. So there are two exercises here, and I hope that through this video your knowledge in calculus will be enhanced and developed. So here is the first problem. Find the equations of the tangents to the curve y equals 1 over square root of x at the points 1, 1 and 4, 1/2. Also sketch the graph showing the two tangents. So take note that the domain of this function is 0 positive. So open parentheses, 0 to positive infinity. 0 cannot be assigned to this curve because it is undefined. But when x is very close to 0 but positive, y is 1 over almost 0, so that's positive infinity. It comes from positive infinity when x is 9, it is 1/3. When y is 1/3. When x is 4, it is 1/2, and so on and so forth. When x is 1, it is also 1. So when x is 25, when x is 1 over 25, so y is 5. Let's go back. When x is 1 over 25, y is 5. When x is 1 over 16, y is 4. When x is 1 over 9, y is 3. When x is 1/4, y is 1/2. When x is 1, y is 1. When x is 4, y is 1/2. And when x approaches infinity, y approaches 0. So the graph would be, if this is the y-axis, the graph would be as shown, and it approaches the x-axis when x approaches positive infinity. And this is the graph or figure for problem B, part B. We will have that later after I discuss the solution to part A. So y is 1 over square root of x, or y equals x to the negative 1/2. Therefore, y prime is negative 1/2 x to the negative 3/2 times 1. Or simply negative 1 over 2 x to the positive 3/2. So that's the formula for the slope. Then when x is 1, y is negative 1 over 2 times 1 to the 3/2. So y prime is equal to negative 1/2. And the slope when x is 4 is negative 1 over 2, quantity 4 to the 3/2. 4 to the 3/2 is 8 times 2, 16. So the slope is negative 1 over 16. So let's focus first on the first tangent to 1, 1, where the slope is negative 1/2. The expected equation of the tangent is x plus 2y equals x1 plus 2y1. So this is the graph. This is the first point of tangency. This is the second point of tangency. So y prime is negative 1/2. So x plus 2y equals x1, which is 1, plus 2 times y1, which is also 1. So x plus 2y equals 3, the first tangent. So the y-intercept is 3/2 or 1.5. It crosses this point, tangent to this point, and we also have x is 3. The tangent passes this point here. So that's the first tangent, tangent 1. And for the second tangent, the slope is negative 1 over 16. the expected equation is x plus 16y equals x1, which is 4, plus 16 times y1, which is 1 half. So x plus 16y equals 4 plus 8, so 12. The second tangent is x plus 16y equals 12. So where is that point of tangency? This one. And the y-intercept is 12 over 16, or 3/4, 0.75. It crosses the point there. And the x-intercept is 12, so somewhere there. X is 12. So that's the second tangent. And this is the graph of y equals square root of x. These are the tangents to the first point of tangency, second point of tangency. So that's it for this part. Let's proceed to part B. The graph shows the position function of a car. Use the shape of the graph to explain your answers to the following questions. What was the initial velocity of the car? So supposedly this is straight. The tangent at the origin, when time is time axis, this is the position axis y, axis s rather. The tangent is horizontal, and the slope of the tangent at the origin is 0. And if the slope is 0, which is interpreted as velocity, because derivative of position s with respect to time is instantaneous velocity. So the velocity at the start, when time is 0, is the slope of the tangent at the start. So since the slope of the tangent to this s versus time curve is horizontal at the start, so that means the velocity is also 0 at the start. So the answer, VO equals 0. Then, was the car going faster at B or at C? Then we will describe the velocity of the car as the slope of the tangent to the curve. At B, the slope of the tangent is positive, but it is almost 0. And as we move from B to C, or B to this point C here, it begins with positive slope, but gentle slope. The slope decreases until there is somewhat almost horizontal tangent here. So that means the velocity is slowing down. It moves because the slope decreases at B, then it means that initially at B it moves with a certain velocity. The slope of the tangent decreases, so it is moving slower at B, or the initial tangent at B, the tangent at B, the slope of the tangent at B is lesser than the slope of the tangent at C. And remember, slope is velocity. That means that the magnitude of velocity at C is greater, because the slope is greater than the slope of the tangent at B. So therefore, the car is going faster at C. So that's our answer. Faster at point C. The car is moving faster at C. Explanation, the slope at B is less than the slope of the tangent at C. Then B.3, was the car slowing down or speeding up at A, B, and C? At A, of course, the tangent is almost steep, almost vertical, so it is going faster at B. It is speeding up at A, and the slope is increasing. At B, the slope of the tangent is decreasing, as explained earlier. And at C, the slope is before C, and after C, the slope of the tangent is the same. So that means it neither slows down or slowed down, or it is neither slowing down at C or speeding up at C. Explanation: this is concave up curve before C, and after C it is concave down. So therefore, the second derivative of, or the derivative of velocity, first derivative is velocity, the second derivative is supposedly acceleration. And because the velocity is before C is the same as after C, the slope of the tangent before C and after C is the same, or the second derivative of S with respect to time is 0. So it is neither slowing down or speeding up at C. So our answer at A, it is speeding up because the slope is increasing. At B, it is slowing down because the slope is decreasing. At C, it's neither slowing down or speeding up because the slope is constant at C. Before and after C, just before and just after C, the slope of the tangent is the same. It's not changing just before and just after. So for our answer for B.2, B.3, it is speeding up at A. Car was speeding up at A. At B, car was slowing down. And at C, it's neither speeding up nor slowing down. Then we proceed to B.4. What happened between D and E? So because the position function is constant at between D and E, so it means that the car did not move between D and E, or the car was at rest. So the car was at rest between D and E. So that's it for this video.